In this video I'll be going through some of the preliminaries necessary to understand the Runge counterpart of the unit Advanced Ordinary Differential Equations and Dynamical Systems. Okay, so I'm going to start by defining an ordinary differential equation, or often known as the acronym ODE. Now, I know you've been working with these for a number of years now, but it's always a good idea just to sort of refresh our memory as to the formal definitions. So an ODE is simply an equation written in terms of some function f, which is a function of an independent variable t, a function which is called y, which is of t, and various derivatives of y. So you can see here, so on the right hand side we have our function f, which is often referred to as the ODE function. On the left hand side we have a derivative of y. So in this case we have the nth derivative of y, and the derivatives of y in the function f can only go up to n minus 1. Okay, well the order of the ODE is simply the order of the largest derivative or the highest derivative in the ODE. So here we can see we have order n, and here we've got n minus 1, so this is an nth order ODE. And the solution to this ODE is this function y. Okay, so that's what we're trying to find. And that will be the solution over some domain of t. Okay, ooh, the wrong way. Okay, well, as it stands in this form, if there is a solution, there are infinitely many solutions which can satisfy this equation. So in order to have a unique solution, which is for practical purposes, that's probably what we want, we need to specify the solution of y at a known solution. Okay, so I didn't explain that very well. I'll start again. Right, so in order to give a unique solution for an ODE, what we need is a known solution of y at some value of t. And usually we choose a value of t which is at the lower bound of our domain. So quite often t is actually time, although it doesn't have to be. So if we know the initial state of a system, i.e. the initial solution, for example, if we know that our solution y at the lower bound t is equal to alpha, this is our initial value. Okay, and we can then write our ODE and include the domain, which is this t min to t max. Okay, so this is the this interval is what we're interested in, and of course the initial value. So this is known as an IVP, and most sort of when we're dealing with ODEs, this is what we're actually saying we're solving. We're solving an initial value problems. Okay, so for example, if you know concentration of substance or substances in a chemical reaction before the reaction has taken place, that's we could solve that using an initial value problem. Okay, one of the unfortunate things about using numerical methods for solving ODEs is they can only cope with solutions of first order ODEs. So if we've got a higher order ODE, what we need to do is rewrite our higher order ODE as a system of first order ODEs. So for example, here we have an nth order ODE, and what we can do is we can split it up by letting, let's say y1 is equal to our function y, y2 is equal to the first derivative of y, y3 is equal to the second derivative of y, and etc. So then what you have is, since y2 is equal to y dash and y1 is equal to y, then the derivative of y1 is equal to y2, and since if we differentiate y2 we get y3, so derivative of y2 is equal to y3, and we can keep going down this way until we get to yn. So the derivative of yn would be equal to our function f expressed in terms of y1, y2, etc. Okay, so on the left hand side we'll have n different values, y1, y2, all the way up to yn. On the right hand side we'll have n minus 1 cases of y2, y3, etc. And on the last equation we'll have our ODE function. So this is a system of n ordinary differential equations, and furthermore these are first order ordinary differential equations. So it means that our numerical methods can be applied to solve these, and the solution is then equivalent to the solution of the higher order ODE. Okay, well, in this part of the course we'll be focusing on Runge-Kutta methods. And Runge-Kutta method is a very common method for solving ordinary differential equations, then generally known as single step methods. And that's because we only need information of a single step in the domain T to calculate a future step. The other type of methods are multi-step methods, which require information from multiple steps to update the solution. Now, Runge-Kutta method, often known as RK for short, the solution of our first order ODE. So here we can see we just got a first order ODE, f of t, which is a variable. Always remember that y is a function of t. For brevity, we often don't actually write the t in brackets after y, but that's something we've always got to be aware of. Okay, so what we do is, if we have a known solution yn at some known or some value in the domain Tn, we can calculate the solution over a single step. Okay, so this is known as advancing the solution by adding this weighted sum to our current solution. Okay, so we can see here we have a summation I equals 1 to s of bi times ki. Now you'll notice here I've got a bi value here, I've got a ci value and aij. We'll come back to these. These are just coefficients. What we have here with the ki is these are known as stage values. So these are intermediate calculations which we need to do in order for us to update yn plus 1. H, this is what's known as a step length. Now this is the difference between our independent variable t at the next step, denoted by n plus 1, and the current step denoted by tn. So tn plus 1 is simply our current value of t plus that step length h. H is normally some small number. The larger the value of h is, the more inaccurate our solution is going to be. So usually h is some small number. We'll talk more about that when we come to deal with adaptive step size control. Okay, so this is how a Runge-Kutta method advances the solution by a single step. You notice this summation extends from I equals 1 to s. Now s is the number of stages we have, and the stage values are calculated using the ODE function. Okay, so this f is comes from this ODE function. So the arguments into the function, okay, instead of t we have our current value of t, which is tn, plus some coefficient ci times our step length h. So instead of t we replace t with that expression, and instead of y we replace it with this expression, and you can see this is another weighted sum. So it's our current solution plus a weighted sum. So again, this is the same step length h multiplied by this summation. Now aij, like ci and bi, is just some coefficient, and kj is what's known as a stage value. Okay, just going to go back to this. Quite often it's very, very common for Runge-Kutta methods to be expressed in what's known as a butcher tableau. So this makes it just a bit easier to compare and a bit easier to write down a particular method. Okay, so I mentioned we had the coefficients a, b and c, so I'm just going to go back a slide. Okay, so the coefficients b, you can see the bi, they're used in the updating of the solution yn plus 1, and the coefficients ci and aij are used in the calculation of the stage values. Okay, now specific values of a, b and c define a particular Runge-Kutta method. So there's lots and lots of Runge-Kutta methods. They'll have different values of a, b and c, and that's what sort of differentiates them or tells them apart. So what we have is A is an S by S matrix. Now S is the number of stage values we have. So here we have some square matrix A. B and C are column vectors, or typically we commonly refer to them as column vectors. So we have an S by 1 vector for B and an S by 1 vector for C. And the butcher tableau is represented in this form. So it's got 4 regions. Okay, the upper left region lists the values of C, upper right region lists the value of A, and the lower right region lists the values of B transpose. So if we expand out the equations for a Runge-Kutta method, so just going back a couple of slides, so you can see here we've got a couple of summations. Okay, so what I've done here is I've expanded out the summations. So this is the summation in the K, or one of the stage values, and this here is the summation in the updating of our solution yn plus 1. So if we express this Runge-Kutta method as a butcher tableau, we have the C values. This is done the this upper left sort of quadrant of our tableau. So these C values, remember, this is what we add or what we multiply by our step length h and add to our value of Tn. We have the A values, so these are all in the calculation of K1, K2, etc. And this is in the upper right quadrant. And the B coefficients, okay, this is what we use in our weighted sum to calculate yn plus 1, and this is in the lower right quadrant. So a butcher tableau is just a convenient way of defining a particular Runge-Kutta method. Now there are two main types of Runge-Kutta methods, and the first one we're going to look at here is explicit methods, often known as the acronym ERK. And explicit methods are where our stage values are expressed using explicit equations. So what I've done here is I've written out a typical or a general form of an ERK method, and what you'll notice is when we calculate K1, it's an explicit relationship. In other words, K1 does not also appear on the right hand side. Okay, so if we write out, if we have K2, now K2, the calculation of this uses K1, but we don't have K2 also appearing on the right hand side. So if we calculate K1, K2, etc. sequentially, we have explicit equations. So going back all the way down to Ks. Now Ks is written in using K1, K2 and all the previous stage values up until Ks minus 1. So this is known as an explicit Runge-Kutta method. If you look at the butcher tableau for an explicit method, we can see that the A values form a lower triangular matrix. So we have 0 values, or I've just not written them down or omitted them here, in the main diagonal and the upper triangular region. Okay, so that's an explicit Runge-Kutta method. The other type is an implicit Runge-Kutta method, or IRK for short. Now this is where the stage values are expressed using implicit equations. So for example, here we have K1. If we were trying to calculate K1, we note that K1 also appears on the right hand side. And same for K2 if we're trying to calculate that, and let's say we don't know what K2 is, but we have a problem because it also appears on the right hand side. So these are all implicit equations, and if we look at the butcher tableau, we can see that the A matrix is no longer lower triangular, so we have non-zero elements on the main diagonal and perhaps in the upper triangular region. So those are the two main methods, explicit methods and implicit. In general, explicit methods are much easier to derive and to apply, but the problem is if we have what's called a stiff system, where stiff system essentially means where the step length h becomes prohibitively small, and implicit Runge-Kutta methods have much better stability, meaning we can use a larger value for our step length h.